Hey everyone, welcome back to another physics past paper video. Today we're going to talk about paper 4 from the February-March 2023 series and variant 4.2. Before we jump into the paper, let us show you some great booster pack that we have developed. This is available on our Patreon page, and you can see that below the video and in the description also what it contains. Definitions and formulae for AS, as you can see, it all goes all the way up to particle physics. So for example, as you can see over here, definitions, key phrases, terms, formulae. Frequently examined questions, they focus on paper 2 part of that. So for example, if we open anything over here, you will see some questions that are quite frequently examined. Then we have important derivations. For example, if we see this over here, you will see the I is equal to NAVE or NAVQ, whatever you want to say it. These are the derivations, all of these that are required by the syllabus. Some of these are there for as an exercise. Some of them are required by the syllabus, and most of them are very frequently examined. Then we have A2 definitions and formulae similar to the AS1. We have terms, their definitions, any formulae, any revision points. Then we have A2 definitions and A2 important derivations. It goes all the way up till quantum physics. So for example, if we look at the capacitance, this is the one, this is these two for capacitors in series and parallel. They're very frequently examined, and it's a very simple one. However, not just this, we have almost every important derivation written over here, and we are adding more. Then we have graphs. We know most of the students struggle with field and potential graphs, whether it's gravitational fields or electric fields. So we have drawn them with their respective expressions, mathematical expressions. So you can make them again, try to make them again on your own also. Then we have frequently examined questions for A2. This is more important for paper 4 practice. As you can see, we have structured it slightly differently. Syllabus content on the left, question, answer, and year on the right hand side. So that means we have tried to cover almost every key syllabus topic or content that is required. So as you can see, there will be some questions where you will see a lot of years written on the right hand side. That means that this type of or this line of questioning is very frequently examined. Then we have paper 5 planning question. This is a sort of like a mental checklist that you can have to make sure that all of your required points are considered. Paper 5 booklet also has some solved examples also from October-November 2024. Alright. And once again, this is available on Patreon. Do check it out. You will enjoy this, and let's jump into the paper. Question number 1. Define gravitational potential at a point. Although this is a very easy definition, some students often do miss out a mark because of one slight detail. Let us show you in the frequently examined questions how to answer it. So, for example, as you can see, a lot of years written on the right hand side, and the list goes down below also. That means it's a question that you should be well versed in. Gravitational potential is the work done per unit mass in moving a mass from infinity to that point in the field. So basically, these are the two points, key phrases that are important. Some students often miss out the per unit mass thing. That just simply becomes gravitational potential energy. So potential is the work done per unit mass in moving a mass from infinity to that point. Now let's go back to the paper and write it. So the gravitational potential is the work done per unit mass in bringing a mass from infinity to that point in the field. Alright. Artemis is a spherical planet that may be assumed to be isolated in space. When they say isolated in space, that means we can use the inverse square laws or inverse laws that govern the gravitational forces and gravitational potential equations that we're familiar with. The radiation with distance x from the center of the Artemis of the gravitational potential phi is shown. Okay. The radius of the Artemis is 4,800 kilometers. Determine the value of phi on the surface of the Artemis. So it just means that we need to see what's the gravitational potential at the surface. So we look at over here. So this is right over here. So this is 3.55. So 3.6, 3.7, 3.8, 3.9. This is 3.55 minus 3.55, 10 raised to power 7. So minus 3.55, 10 raised to power 7. Okay. Show that the mass of the Artemis is 2.55, 10 raised to power 24 kgs. Now let's write this. So phi, we know that that is gm over r, so therefore m would be phi times by r over negative g. So let's fill in the values. Phi, we found it to be 3.55, 10 raised to power 7. Radius 4,800 kilometers, so 4,800, 10 raised to power 3 divided by minus g, which is minus 6.67, 10 raised to power minus 11. Alright, so now all we have to do is to plug into the calculator. So 3.55 times by 4,800 divided by 6.67 times by 10 raised to power 7 plus 3 plus 11. So as you can see, 55, 10 raised to power 24 kgs. Now, calculate the gravitational field strength G on the surface of Artemis. Now, two ways to figure this out. We now have mass, so we can do the G equals to gm over r squared. This is one way of doing this. Another way you can see this is that phi is gm over r itself. Okay, the magnitude of that. So we just need to multiply the phi with another r. Both ways you will get the same answer. You can try that also. So let's try that. 6.67, 10 raised to power minus 11. Mass is 2.55, 10 raised to power 24. The values will be very slightly different because we are using 2.55 rounded value. 10 raised to power 3 whole squared, and the other way we said was 3.55, 10 raised to power 7 divided by 4,800, 10 raised to power 3. Okay, now let's see which if we get the same thing or not. 2.55 times by 6.67 divided by 4,800 squared times by 10 raised to power minus 11 plus 24 minus 6. So you get 7.38. Let's see whether we get the same thing on that also. 3.55 divided by 4800 times by 10 raised to power 7 minus 3. As you can see, 7.395 to two significant figures. This is almost similar. 3839, so that's 7.4 Newton per kg. Okay. A satellite is in an orbit at a fixed position above the Earth on the surface of Artemis. The satellite is located above the equator of the Artemis at a height above the surface where the gravitational potential is this. Calculate the period in hours of the rotation of the Artemis. So, first off, we know that phi is basically the minus gm over r, which is the radius of the orbit. However, we don't know r because the relationship between the time period and r cubed is basically like this: 4 pi squared over gm r cubed. We don't know that. So first let's plug in the r over here. So you will have t squared equals to 4 pi squared over gm. R is minus gm over phi minus gm over phi cubed, right? Okay, so one of the gm's will get cancelled, so we will just have left the 4 pi squared over nothing times by there's going to be a minus over here, so we don't have to worry about anything. Gm whole squared times by negative 1 over phi cubed. Okay, so let's fill in the values. So 4 pi squared, gm is 6.67, 10 raised to power minus 11. Mass was 2.55, 10 raised to power 24 squared times by minus 1 over phi is 0.65, 10 raised to power 7. Minus minus will basically look like this. Okay, so minus minus will get cancelled. Now let's find out. So 4 pi squared times by the square root of 6.67 times by 2.55, 10 raised to power minus 11 plus 24 whole squared times by, actually just simply divided by 0.65, oh sorry, 0.65 times by 10 raised to power 7 whole cubed. Okay, so we need to convert it into standard form, so let's do that. So as you can see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 4.2, 10 raised to power 9 seconds. This is in seconds. We need to convert it into hours. So whatever the answer is, we divide by 3600 into this. So this is 1, 2, 3, 4, 5. Oh, sorry. No. Even before that, first off, we need to take the square root. Okay. So answer, just to make sure that this is the same thing, right? Okay. So square root of the answer, that is your time period. Okay, so time is 64.487 seconds. which we now need to convert into 30 divided by 3600. As you can see, this is 17.9 hours. We can convert it into 18 hours. Alright, let's carry on. State one similarity and one difference between gravitational potential due to a point mass and electric potential due to point charge. Now there are several similarities. Both G gravitational potential is inversely proportional to R, and electric potential is also inversely proportional to R from the center of the point mass. Phi is basically always negative, but V can be negative or positive based on the charge. Okay? If the charge itself is positive or negative, that will be negative or positive. So this is the difference. This is similarity. Okay. So we can say both are inversely proportional to the square of distance from the center of point, either it's point mass, point charge, so let's call it point source. Difference being gravitational potential is a negative quantity, while electric potential can be positive or negative. Okay, that's it. That's it for the first question. Let's move on to the second one. Question number 2. State what is meant by an ideal gas. So there are two ways to answer this. Either we say PV proportional to T, or we can say PV over T is constant. Either way, we need to define what PV and T actually mean. Otherwise, this will not be complete. The statement, the definition of an ideal gas will not be complete. So you can write it this way, you can write it this way, so either that's fine. Let's write it the second way. So an ideal gas is one that obeys PV over T, PV over T is constant, where P is pressure, V is volume, and T is absolute thermodynamic temperature of the gas. Okay. A fixed amount of helium gas is sealed in a container. Helium gas has a pressure of 1.1 10 raised to the power 5 pascals and a volume of 540 centimeter cubed at a temperature of 27 degrees Celsius. Okay, now one thing you have to remember, T is the absolute thermodynamics, so this will need to be converted in Kelvin. The volume of the container is rapidly decreased to 30 centimeter cube. The pressure of the helium gas increases to this, and temperature increases to 742 degrees Celsius. Alright, so they have actually given this as a summarize the changes also. No thermal energy enters or leaves the helium gas during this process. Show that the helium gas behaves as an ideal gas. So that means we need to show that PV over T is constant. So there are two ways you can show that. You can show that P1 V1 T1 is the same as P2 V2 T2, or you can show that the difference between them is 0 or approximately 0. So let's calculate that. 1.10 10 raised to the power 5. Volume needs to be, actually, although since this is a ratio, it doesn't matter, but still it would be better if we maintained 10 raised to the power minus 6 to convert it into meter cube. Then we have temperature, 27 plus 2273.15 minus 6.70 10 raised to the power 6 times by 30 times by 10 raised to the power minus 6 divided by 742 plus 273.15. So let's check it out. 1.10 10 raised to the power, actually, times by 540 times by 5 minus 6. Okay, 27 plus 273.15 minus 6.7 times by 30. 10 raised to the power 6 minus 10 6, it's just 0, so it would be just 1. 742 plus 273.15. Now you see this value is extremely low. That means it's almost 0. So you can see 1, 2, 3, 4 decimal places. So this is almost approximately 0. So helium behaves like an ideal gas. Okay, the first law of thermodynamics may be expressed as delta U plus Q plus W. Use the first law of thermodynamics to explain why the temperature of the helium gas increases. Okay, so one thing, Q is 0 because no thermal energy enters or leaves the helium gas. However, the work done on the system will be positive because we are compressing the gas. So the pressure is also not constant. Pressure is not constant. So we can't use the P delta V either because pressure is not constant. So compression is done, so work is done on the system. So that means that the delta U, internal energy rises. Now, for the ideal gas, we know that the internal energy is directly proportional to kinetic energy, average kinetic energy of particles, which is proportional to temperature, absolute temperature of the gas. So if the internal energy is increasing, average kinetic energy is increasing, and therefore temperature of the gas will also increase. So let's say work is done, work W is done on the gas during compression, while no change, no heat or thermal energy Q enters or leaves the system. So the internal energy U rises, which increases the average kinetic energy of particles, and therefore the temperature of the gas. Okay, so you can also squeeze in a point that the internal energy of the gas is directly proportional to kinetic energy of the particles and therefore temperature of the gas. You can also squeeze that also. Right. Okay. The average translational kinetic energy EK of a molecule of an ideal gas is given by this, okay, where K is the Boltzmann constant, T is the thermodynamic temperature. Calculate the change in total kinetic energy of the molecules of the helium gas. That means we need to multiply the number of particles with it. So we don't know n yet. So one thing you can do is you can find out the n from the state equation nkt. So that means you can find out n first by doing PV over KT, and then use that to figure out n times by EK. So 3 by 2 NKT. Now, in all of this, N and K are constant, right? So these two are constant. The only thing that's changing is T. So that means if we can also show this with respect to PV. So since we need the total change in kinetic energy, basically we would be doing NKT1 minus NKT2 or NKT2 minus NKT1. So basically it's P1, V1, T1 that are equal. N and K are already constant. So we can do this with P1 and V1 also. So we can do 3 over 2 P2 V2 minus P1 V1. You can also do it this way. You can also do it by finding 3 over 2 by using the same n that you calculated over here, n k T2 minus T1. Okay, now let's try both of these methods and see whether we get the same answer or not. Okay, so let's try the first one. Let's use, okay, so 3 over 2 P2 was 6.7 times by 30, so 10 raised to power 6 minus 6 minus this P1, basically we have on the left side, I don't need to rewrite it, 1.1 times by 540, 10 raised to power 5 minus 6. This one on the other hand, 3 over 2. First off, we need the n. Okay, so PV over T. Okay, KT. So do we know the value of K? We can check this from the formulas. Oh, sorry, the constants table. And there it is, 1.38 10 raised to power minus 23. So going back, so 1.38 times by 10 raised to power minus 23, this. So PV for one of these situations will get us n. As you can see, this is our n. So n is 1.4 10 raised to power 22. K was 1.38 10 raised to power 23. The change in temperature is going to be the same as change in temperature for the Celsius, because 1 unit of Celsius is same as 1 unit of Kelvin. 742 minus 27. Okay, let's see whether we get the same values or not. So 1.5 times by 6.7 times by 30 minus 1.1 times by 540. Okay, times by 10 raised to power minus 1. 212.4. Let's see this one. I'm sorry, 1.5 times by 1.43 times by 10 raised to power 22. Since we are rounding up numbers, we might get very slight difference, but more or less it will be the same. Times by 742 minus 27. No. Oh, no. Times by 211.6, which is approximately same as 212. So 210 to two significant figures, they are both the same. Had we used for like the more decimal places for the number n, 434, actually we can see we can replace it with the answer, since we have the answer over there. You see, actually we get a better. Even this was fine, not a big deal over here. But you can see that if we use the n properly, you will get 202.24 also. So almost the same thing to two significant figures. Okay, the mass of the nitrogen gas in another container is 24 grams at temperature of 27 degrees Celsius. The gas is cooled to a boiling point of 196 Celsius negative. Assume that all gas condenses to a liquid. For this change, the specific heat capacity of the nitrogen gas is this: the cooling point and the cooling phase. The specific latent heat of vaporization of nitrogen is this. Okay, so the condensation. Determine the thermal energy kg removed from this nitrogen gas. So this is quite easy to do. The change in energy will depend on the energy change resulting from the cooling phase, where the temperature is changing, and then the conversion of state, which is just simply ml. So mass is 24 10 raised to power minus 3. Specific heat capacity is 1.04. Since we need it in kilojoules, we can keep this both in kilojoules also. Times by change in temperature, 27 to 196. You see, so from 27, so basically this would be 27 plus 196. 223 plus same thing, 24 times by 10 raised to the power minus 3 times by 199. So you have 24 times by 10 raised to the power minus 3, 1.04 times by 223 plus 199, you get 10.342 joules, so 3 significant figures, so 10.3 joules, kilojoules. Sorry. And that's it for question number 2. Let's move on to question number 3. Question number 3. An object is suspended from a vertical spring as shown in figure 3.1. The object is displaced vertically and then released so that it oscillates, undergoing simple harmonic motion. Figure 3.2 shows the variation of displacement x of the energy E of the oscillations. Okay. The kinetic energy, the potential energy, total energy of the oscillations are each represented by one of the lines PQR. State the energy that is represented by each of the lines PQ and R. Okay. The first one is easy. P is the total energy of oscillations. So total energy of oscillations. Now Q and R. So we know the V or V squared is related to omega squared, x naught squared minus x squared. Okay, we are already familiar with this. You may have seen this as omega plus minus x naught squared minus x squared also. So basically what that just means is this is the V with respect to x and x naught. So if you multiply the half m with this, you get the kinetic energy, half m v squared. This would become half m omega squared x naught squared minus x squared. So basically this means that due to this factor minus half m omega squared x squared, this factor means that this is going to be inverse quadratic. Sorry, no, not inverse. It's a inverted U-shaped quadratic parabola. Similarly, potential energy. We already know that potential energy will depend on the difference or the distance from the mean position. So that is just simply half m omega squared x squared. That means this is quadratic, simply quadratic. And other things you may remember is that potential energy will become 0 at the mean position when it is passing through the mean position. So that means Q is the potential energy, and kinetic energy at mean position when it's passing through the mean position during the oscillation state will be highest. So R is the kinetic energy and Q is potential. And R is kinetic. Okay, so Q and R, right, okay. The object has mass of 130 grams. Determine the period of oscillations. We can only determine the period of oscillations if we know omega. Okay, so first off we need to find out omega. So we can do that by using the total energy, half m omega squared x naught squared. That's the maximum kinetic, maximum energy, maximum kinetic, maximum potential. So we need to find out the omega squared first. So 2e over m x naught squared 2 times by let's say this is 6.4 mJ millijoules divided by mass is 130, so 0.130 basically 123 kilograms, and the maximum displacement is basically this thing. Let's calculate this. So this is 1.5 centimeter. So 1.5 10 raised to the power minus 2 whole square. Okay. So 2 times by 6.4 divided by 0.130 divided by 1.5 squared times by 10 raised to the power minus 3 plus 4. You get this is again omega squared, not omega itself. Okay, so therefore the omega will be the square root of this thing, 20.919. So t would be, time period would be this thing. So 2 pi divided by answer, you get 0.3 seconds. Okay. State the cause of damping. The damping is actually caused by energy loss due to resistive forces. So loss of energy of oscillation due to resistive forces. Okay, a light card is attached to the object, this thing. The object is displayed with same initial amplitude and then released. During each complete oscillations, the total energy of the system decreases by 8% of the total energy at the start of the oscillations. Determine the decrease in total energy in mg. We need to find out the decrease by the end of the first 6 complete oscillations. So what you can do is figure out the total energy. Okay, so total energy remaining after 6 oscillations. So this is like compounding percentages problem. Decreases by 8%, so you still have 92% times by total energy. Oh, sorry, we have to do this 6 raised to the power 6 also. And the total energy that we found was 6.4 millijoules. Okay, so 0.92 raised to the power 6 times by 6.4 times by 10 raised to the power minus 3. So you get total energy. We can do this in the mj also, because we need this in mj, millijoules. So 3.88 millijoules. So decrease in energy would be difference between these, 6.4 minus 3.88. So 6.4 minus answer is 2.59. 2.519, so that is basically just 2.5 mj, millijoules. State with a reason the type of damping that the card introduces into the system. Okay, now if you notice over here the calculation that we did, another way to do this is 6.4, 1 minus 0.92 raised to the power 6. So focus on this thing. So when we do 1 minus 0.92 raised to the power 6, if you times it by 100, it's just 39%. Okay, so just 39%. So you can check that also. So 6.4 times by a 39% decrease. So 1 minus 0.39. So roughly we will get 3.88 or 3.9, whatever. So that means basically that was something 0.92 raised to power 6. So as you see over here, the decrease is very gradual. Okay, so this is just 8% decrease every time. So as we go for example 10 oscillations, it has barely just gone up till 56. When we go for example 100 oscillations, then you will see almost all the energy gone. So for example, let's say between 50 oscillations, you see it's very gradual because of the 8% decrease. Now that means that this is a light damping. Okay, so it is light, sorry, we can say that this is the gradual decrease in energy, because you see it's basically 0.92 raised to power x. Okay, so if you sketch that, it's a gradual decline. So basically, actually the better way would be to just focus on the 0.92, because this is how the reduction is happening. So this is basically going like this. Oh sorry, no, like the exponential decrease basically, because this factor is less than 1. So the gradual decrease in energy indicates light damping. As 8% decrease in energy would cause a very gradual decline, a very small decline in amplitudes every oscillation. Okay, now there's another way to see this through also. If you so total energy is basically half m omega squared x naught squared. So basically the energy itself is proportional to x naught squared, the amplitude squared. So if the energy is decreasing with a factor like this, that means the maximum amplitude is also decreasing with a factor like this. So notice that this is a square of that oscillation. So basically the change, if you want to see the amplitude, this is proportional to the square root of the energy. So the changes in energy are actually proportional to the square root of oscillations. That is an important point to write over here also. You can write that definitely. That the amplitudes is proportional to the square root of energy. The gradual decrease, 8% decrease, the gradual 8% decrease in energy will create a very small decline in amplitudes every oscillations. So that is an important point you can write also. Alright, so that's it for this question. Let's move on to the next one. Question number 4. State Coulomb's law. Now this is also an important definition. We can see that in the frequently examined questions. However, let's try to write this. So it states that the electrostatic force between point charges is proportional to product of the charges and inversely proportional to the square of the distance between their centers. Distance between their centers. Okay. A charged sphere X is supported on an insulating stand. The second charged sphere Y is suspended by an insulating thread, so that sphere Y is in equilibrium at position shown. The charge on sphere X is plus 96 nanocoulomb. The charge on the sphere Y is 64 nanocoulombs. Assume that the spheres behave as point charges. The length of the thread is 1.2 meters, and the centers of the spheres X and Y are separated by horizontal distance of 0.08 meters. Okay. On figure 4.2, draw and label all the forces acting on the sphere Y. Okay. So weight first, easiest one to figure out. Weight. There's going to be a tension force in the string. Then you will have the electrostatic force of repulsion. Electrostatic force. And this is the force of repulsion, basically. So, okay, that's it. Determine the mass of the sphere Y. So, this is mass will come from mg. To do that, we actually have to figure out the angles working over here. So this angle would be basically the same as this angle. Actually, sorry. Right, okay. So this angle would be the same as this angle, because this is the vertical component and this is going to be the horizontal component. Okay, so let's simplify this a bit. So let's say this is T, let's say this is F. Okay, so this is going to be, let's say this is theta, this is T cos theta, T sine theta. Okay, we also know these sine and cos theta basically, right? So because they gave us every information. So this is 0.08, length is 1.2. So this angle, we can figure out the Pythagoras, basically simple maths. Pythagoras 1.2 squared minus 0.08 squared, so that is 1.197. So now we can come up with sine theta, 0.08 over 1.2. Cos theta would be 1.197 over 1.2. And tan theta, so you can see this is 1.197, this is almost 1.2, but I'm going to keep it this way as best as possible. 0.08 over 1.197. Okay, now T cos theta, sorry, first off, T sine theta is the, you see the force of electrostatic force is K Q1 Q2 over R squared. K is that constant, and the T cos theta is equal to mg. Okay, so one easy way to figure this out, because we don't need to know the t, we cancel out this, and this becomes just simply tan theta equals to basically mg tan theta becomes k q1 q2. We need the mass, so therefore mass becomes k q1 q2 g tan theta. Okay, now we plug in the values. K is 8.99, 10 raised to power 9, 64 and 96, right? 96 and 64, okay. 64, 96, and they're both minus 9 microcoulomb, nanocoulomb divided by G 9.81 tan theta. We wrote the here 0.08 divided by 1.197. basically this would go on the numerator, 1.197. Okay. So did we calculate this? No. So 1.2 whole squared minus 0.08 whole squared. Both were in meters. Okay, so let's keep this as it is. Alright, so you have 8.99 times by 64 times by 96 times by answer divided by 9.81 divided by 0.08 times by 10 raised to the power 9 minus 9 minus 9. The mass is 1, 2, 3, 4. Wait. Oh, we forgot about the r squared. Oh, over here you have r squared also. Okay, my bad. This is 0.08 r squared. So we can actually make this factor cubed. So right, okay. So 0.01316.7. So we already took care of this units, so that means that we have it in kg. So 0.013. Okay. Calculate the total electric potential energy stored between x and y. So EP basically is just K Q1 Q2 R. Okay. Is there anything that we have calculated that can help us? Because this is 1 mark, although the calculation is fine, but there should be something. Okay, never mind, we can just simply calculate it. So 8.99, 10 raised to the power 9, so okay, yeah, so basically there is a way, so we can replace the KQQ with mg tan theta. Okay, sorry, this is over r squared. Okay, you can replace the KQ Q1 Q2 over r squared. For that you can multiply this with r both sides to get that, but anyways that seems like a longer calculation. So you have 64, 96, 10 raised to the power minus 9 divided by 0.08. Alright, 8.99, 10 raised to the power 9 times by 64 times by 96 divided by 0.08. We go back in the power, minus 9, you get this value, 1, 2, 3, 4, 6.9, 10 raised to the power minus 4. Okay, moving on. An electron enters the region between two parallel plates P and Q that are separated by a distance of 18 mm as shown in figure 4.3. Space between the plates is a vacuum. Potential difference between the plates is 250 volts. Electric field may be assumed to be uniform in the region between plates and the zero outside the region. State the region of the electric force on the electron between the plates. Okay. So the field direction, so the point where the student get confused, field direction is downwards, and since this is uniform field lines, if we had to draw, they will be parallel and almost equidistant. Now field direction is the direction of the positive charge. This is an electron. Electron will be attracted to the positive side. So we will say upwards. Okay. Determine the magnitude of force acting on the electron due to electric field. So basically force is QE and this will be QV over D. So charge on the electron is 1.6, 10 raised to the power minus 19. Potential difference is 250. Distance between them is 18 millimeters. So 18, 10 raised to the power minus 3. So 1.6 times by 250 divided by 18 times by 10 raised to the power minus 19 plus 3. You get this. 2.22 10 raised to the power minus 15. So 2.2 10 raised to the power minus 15. Explain why the electron does not follow a circular path. So remember, for circular path, the direction or the angle between velocity, acceleration and force has to be 90 degrees at all times. Okay, so the force is only initially perpendicular to force, or acceleration is always just in this direction, but velocity is changing direction all like this, but force and acceleration will remain in single direction. So that is the reason. So the force acting on the electron remains in a single direction, force acting on the electron remains acting in single direction, and not always perpendicular to electron's velocity. Alright, and that's it for this question. Let's move on to the next one. Question number 5. A capacitor, a battery of electromotive force, EMF 12 volts, a resistor R and a two-way switch are connected in circuit shown in figure 5.1. Switch is initially in position S. When the capacitor is fully charged, the switch is moved to the position T so that the capacitor discharges. At time T, after the switch is moved, the charge on the capacitor is Q. The variation with T of ln Q microcoulomb is shown in figure 5.2. Show that the capacitance of capacitor is 1.5 microfarad. So remember that when it is fully charged, okay, so when fully charged, you have Q naught is equal to C V naught. Okay, so if we want to find out C, we need to find out maximum charge and divide it with maximum potential difference, which is 12. We need to find out the maximum charge. So maximum charge is starting from 2.9. This is the already ln Q. Okay, so you see this, that ln of Q is 2.9, right? So that means we need to reverse that. So Q naught would be e raised to power 2.9. So e raised to power 2.9, this is already in microcoulomb, divided by 12 volt. So we should get in microfarad also. So e raised to power 2.9 divided by 12, that is 1.5 microfarad. Okay, determine the resistance R. Resistance R we will get from the time constant RC, and for that we need the gradient, because why? Q is equal to Q naught e raised to the power minus t over tau, time constant. When you take ln, this becomes ln Q naught minus 1 over tau t. That means this thing is your gradient. If we can find out the gradient, we can find out the RC. We also know the C now. Okay, so this is your 2.9 that we figured out, the y-intercept. We just need to find out the gradient. Okay, so we we have the 2.9 over here. Now we need another point, any other point, any reasonable point over here, like this one over here. This is 4, 1.9. Okay, 4 seconds, 1.9. Let's see that. So gradient is equal to minus 1 over tau. That is 1.9 minus 2.9 over 4. So minus 1 over 4 basically. Therefore tau is 4. So R would be 4 divided by 1.5 microfarad. Sorry, no. Yeah. I was right, sorry. 1.5, 10 raised to power minus 6. Okay, so 4 divided by 1.5 times by 10 raised to power 6. This is, we need to write it in standard form. This is millions, so 10 raised to power 6. So 2.7, 10 raised to power 6. Calculate the energy stored in capacitor at time t is equal to 0. So that comes from maximum energy. So QV or Q naught V or half C V naught squared. Either way, we know both of those things. So half capacitance is 1.5 microfarad and V is 12 volts. So 0.5 times by 1.5 times by 144 times by 10 raised to power minus 6. So 1, 2, 3, 4. Okay, we can test out with the other also. Half Q naught, so half. This was e raised to power 2.9. This was in microcoulomb, so we need it in coulombs, and 12. So e raised to power 2.9, 12. As you can see, we're getting the same thing. So 1.1, 10 raised to power minus 4 joules. A second identical resistor is now connected in parallel with R. Switch is initially in position S. When the capacitor is fully charged, the switch is moved to position T so that capacitor discharges at time T. After the switch is moved, the charge on the capacitor is Q. On figure 5.2, sketch a line to show the variation of this between t is equal to 0 and 5 seconds. Okay, to understand that, when the two resistors are connected in parallel, this is R, this is R, so the effective resistance is half of one of them, right? So that means the time constant, which is the effective resistance times by the capacitance, is reduced by half also. So that means the gradient, which was already -1 tau, this becomes -2 RC. Okay, so that means this thing means that it will have double the gradient. So over here where we had 1.9, the decrease was like 1, rise over run basically. We need to go further at 0.9 at 4 seconds. So it will be over here. So at 5 seconds it would be right, like this. It will originate from the same point because the rest of the conditions is the same. V is the same, initial V is the same, but it will have a higher time constant. And that's it for this question. Let's move on to the next one. Question number 6. A Hall probe is placed in a magnetic field. Hall voltage is 0. Hall probe is rotated to a new position in magnetic field. The Hall voltage is now maximum. Explain these observations. Now this is an important point for paper 5 also. So when the magnetic field is parallel to the Hall probe plane, it will register 0, and when it is perpendicular, it will register maximum. So that's why in paper 5 you will also see wherever we are using Hall probe, we rotate that Hall probe to make sure we have the maximum value. So Hall voltage is 0 when the plane of Hall probe is parallel to magnetic field whereas its maximum when the plane of the probe is perpendicular to magnetic field. Okay. The formula for calculating Hall voltage VH is measured as this again. Table 6.1 shows the value of N for two materials. So this is number density and number of charge carriers per meter cube. State the meaning of M. Number density, which is number of charge carriers per unit volume. Sorry, did I say area? Per unit volume. Okay. Explain why a Hall probe is made from silicon rather than copper. So this is basically, you can see this from this. So Hall voltage is inversely proportional to the number density. So lower the number density, higher the changes in Hall voltage, or higher the Hall voltage that will be registered. So lower the number density, of a material. Actually, the lower number density of copper, sorry, we can specify that. The lower density of silicon, sorry, will produce higher values of Hall voltage. Okay, all right. A Hall probe gives a maximum reading of 24 millivolts when placed in a uniform magnetic flux density of 32 millitesla. Same Hall probe is placed in a magnetic field of fixed direction and varying flux density. Hall probe is in a fixed position so that the angle between the Hall probe and the magnetic field is same as when Hall voltage was 24 millivolts. So basically it's placed in the same orientation. Variation of the reading VH on the Hall probe with time t from t is equal to 0 to t equals to 8.6 seconds is shown in figure 6.1. Okay. Coil with 780 turns and a diameter of 3.6 centimeters placed in this varying magnetic field. The plane of the coil is perpendicular to field lines. Calculate the magnitude of maximum electromotive force induced in the coil. Alright, so first off we need to see what this corresponds to, what magnetic flux density this corresponds to. So we know that VH is basically proportional to B. Everything else is the same. Okay. Orientation is the same, fixed direction, right? So this is perpendicular to that. So basically it's a ratio. So V1, B1, V2, B2, sort of that thing, right? So you have 24 when the field strength was 32. Now we need, this is 36. So we need to know what is B now, right? So this would be 32 times by 36 divided by 24, so B is now 48. Simple math over here, simple ratios. So B is now 48. So this corresponds to 48 millitesla. So at 36 millivolts, B is equal to 48 millitesla. Okay, so the maximum magnitude of electromotive force will come from the greatest change in B over T. Greatest, because you see EMF is directly proportional to the N BA over T, right? The change in this. N and A are not changing, so basically it's just directly proportional to change in B over T. So greatest increased. So greatest rate of change is happening this way. So if we figure out how much duration this happens, so we can figure that out. So this is 8.6 and this is 7.2. Okay, so 8.6 and 7.2, the change is basically this. So EMF is equal to N A change in B over change in T, so 780 turns. Area is this, so which would be pi d squared over 4, so pi 3.6 10 raised to power minus 2 whole squared over 4, and this is we need it in volts basically, so 48 millitesla minus 0, and from 8.6, 7.2 seconds, right? Right, okay. So now we need to calculate this. So 780 times by pi times by 3.6 whole square, actually wait, 3.6 whole squared, times by 10, no wait, 48 divided by 4 divided by 8.6 minus 7.2, 3.6 whole squared, 48 divided by 4 divided by this. Now the powers of 10, minus 4 minus 3, that's it. So that is 0.02722, so that is 0.027 volts. And that's it for this question. Let's move on to the next one. Question number 7. A beam of white light passes through a cloud of cool gas. The spectrum of the transmitted light is viewed and contains a number of dark lines. Explain why these dark lines occur. Now what happens is that when the light passes through this cool gas, some of those frequencies or wavelengths will get absorbed by the electrons. So for example, you have this electron over here. When it absorbs a photon, it jumps to a higher level. That means it excites. But since this is an excited state, it will want to return to a lower energy level. Maybe there's an energy level in between also, or to a ground state. So either way, photon will be released. So the problem with this is that the released photon will be in random directions. So the intensities received at the screen will have a lower intensity recorded, and the lowest intensity recorded for the ones corresponding to the ones that were absorbed. So that is why they will appear as dark lines on the continuous spectrum. Okay, so that's all that we have to write. And just to show you that we also have the similar thing in the grade booster pack also, so let us just show you quickly and then we will write it. So as you can see, this is not just in February, March 2023, this is a question that comes up. So the dark lines in the spectrum of transmitted light occur because photons are absorbed by electrons in the gas, exciting the electrons to higher energy levels. When these electrons de-excite, they emit photons with energy equal to the difference in energy levels in random directions, basically over here, and resulting in dark lines in the spectrum. Okay, so that's what we just need to write. So when light passes through the gas, the electrons in the gas particles absorb some of the wavelengths, some of the photons, energies, and transition to higher energy levels. The energies absorbed are equal to differences in energy levels these excited electrons then de-excite releasing energy in the form of photons of specific wavelengths corresponding to difference in energy levels again. These photons are released random directions therefore the intensities of these wavelengths will be on the spectrum and hence appearing as dark lines on spectrum. Okay, sorry. Alright. Some energy levels for the electron in an isolated hydrogen atom are illustrated in figure 7.1. The table 7.1 shows the wavelengths of photons that are emitted in transitions to n is equal to 2 from other energy levels shown in 7.1. The energy associated with level n is equal to 2 is minus 3.40 electron volts. Okay. Calculate the energy in joules of the energy level n is equal to 3. Okay, so remember these wavelengths correspond to energies transitions to n is equal to 2. That means no other transitions, only to n is equal to 2. So if we want to figure out the energy level of n is equal to 3, that means this one, we need to figure out the wavelength first. So as we said over here that the wavelengths correspond to the energy differences. So we know the wavelength energy is equal to hc over lambda, so that means inversely proportional. So the lowest energy difference would mean the highest wavelength. So highest wavelength in this would be 658. Now furthermore, how do we take the energy level now? Okay, so let's say this is, let's say, E3 and this is your E2. Okay, so when it goes from E3 to E2, you're actually taking energy away. Okay, so basically from E3 you are reducing energy to get to E2. So they're already negative. Okay, so they're already negative, and that's what you're doing. So that means the energy level, the difference in energy level would be minus E3 plus E2. Or you can say the minus E3 minus E2. Either way, that will get you the right answer. Okay, so that will be the difference in energy levels. But since we actually need this thing E3, right? So we can keep it this way also. So if we rearrange this, so minus E3, this will be minus E2 minus the difference in energy level. So first off, we actually basically need the energy level. Okay, so we basically need the energy level. So we will go back and make it the same as before, as we wrote. So the difference in energy level, which is equal to hc over lambda, will be equal to minus E3 minus E2. Okay, so minus E3 minus E2 is equal to hc over lambda. So that is basically what we just simply need. So minus E3 is equal to 6.63 10 raised to power minus 34 Planck's constant, speed of light, sorry, 3.0 10 raised to power 8, wavelength 658 nanometers, and this goes plus minus 3.4 electron volts. So this is 1.6 10 raised to power minus 19. So this will now be in joules. Okay, now let's calculate this. And 6.63 10 raised to power minus 34 times by 3 times by this divided by 658 times by, now we do the powers, minus 34 plus 8 plus 9 minus 3.4 times by 1.6 10 raised to power minus 19. And that's it. In the negative form, 2.417 10 raised to power minus 19 minus 2.42 10 raised to power minus 19. Okay, that's it for this question. Let's move on to the next one. Question number 8. Plutonium-238 is unstable and undergoes alpha decay. Complete the equation to show the decay of plutonium-238. So alpha particle is basically, we already know that this is just a 4-2. That means the mass number decreases by 4 to 234, and proton number decreases by 2 to 92. Power source in a space probe contains 0.874 kgs of plutonium-238. Each nucleus of plutonium-238 decays emits 5.59 mega electron volts of energy. Half-life of plutonium-238 is 87.7 years. Calculate the initial number N0 of nuclei of plutonium-238 in power source. So one method is by using Avogadro's number, the other is using 238 and the mass of proton numbers. So first off, N, we know that it is number of moles times by Avogadro's number. So 6.02 10 raised to power 23 times by number of moles converted into grams first, 874, divided by this in grams 238. So 6.02 10 raised to power 23 times by 874 divided by 238. So you get this 2.2 10 raised to power 24. Now let's try another method. What if we divide this total mass by the mass of 238 atomic mass unit? So 0.874 divided by 238 U, which is 1.66 10 raised to power minus 27. So hopefully we should get the same answer. 874 divided by 238 divided by 1.66 times 10 raised to power 27. Oh, sorry, my bad. This is also divided by that. Right, so as you can see, we are getting the same answer. So 2.2 10 raised to power 24. 2.2 10 raised to power 24. Determine the initial activity of the source. So we know activity is lambda n. Okay, lambda is the radioactivity constant. And how we find the lambda? They gave us the half-life. Okay, so lambda is equal to ln2 over half-life. So initial activity would be ln2 over 87.7 years. That means we need to convert it into seconds. So this is years, 365 days, 24 hours, and 3600 seconds per hour times by 2.2 10 raised to power 24. So we keep this saved. So ln2 times by answer divided by 87.7 divided by 365 divided by 24 divided by 3600, we get so let's convert this into 554 1 2 1 3 6 9 12 and then 14. Okay, so they're giving us in three significant figures, so we can write 5.54 10 raised to power 14, and the unit for activity is either per second or becquerels. Okay, use your answer in B to determine the initial power output from the source due to the decay of plutonium-238. So power will come from energy, 5.59 mega electron volts. We need to convert it into joules. So activity, you already know that this is basically the dN related to dN over dt, right? So this is the rate, number of nuclei decaying per unit time. So the per unit time aspect of the power will be covered by that. So the power will be activity times by the total energy. One nucleus. Okay, so we have this many nuclei decaying per unit time, and we have energy 5.59 mega electron volts. So that means we also need the energy of one nucleus. Okay, so power is equal to activity 5.54 10 raised to power 14 5.59 first the mega and then the electron volts. You can also convert it one time 1.6, 10 raised to power minus 19 plus 6 minus 13. Either way, that's fine for you. So 5.54 times by 5.59 times by 10 raised to power 14 minus 13. So this is 309.6, so this is 310 output. Sorry, I forgot the 1.6 over here. Right, 495. Okay, alright, let's continue. The space probe will continue to function until the power output from the plutonium in the source decreases to 65.3 of its initial value. Okay, calculate the time in years for which the space probe will function. Okay, so basically we need until the power output decreases that. So initial power output is 495. So we can see over here that power output is proportional to activity. So if you can figure out where activity drops to, what was the percentage? 65.3% of its value, we can figure this out. So we will use this equation minus lambda t. So a over a naught, they're giving us 65.3. So 0.653 is equal to e raised to power minus lambda t. And where lambda is ln2 over half-life, which is, okay, we need this in years, so I think we can use the half-life in years. Okay, 87.7, right, okay. So this would mean that to find out t, for a particular t, we would need to invert this. Sorry, no. I mean, we need to take logarithm of this. So ln and ln of this side, ln of this side, basically. It's not exponent, sorry. It's just ln of this, ln of this. So this would mean that you have t is equal to ln 0.653 divided by minus lambda would become product with t. So you have minus ln2 divided by 87.7. So that's what we need simply. So ln 0.653 divided by minus ln2 divided by 87.7. So we get 53.9. 53.9 years. Three significant figures, so I think we can use three significant figures. Okay. An alternative power source uses energy generated from the radioactive decay of polonium 210. The isotope has a half-life of 0.378 years. The mass of the isotope needed for the same initial power output as in B is 3.37 grams. So just one advantage and one disadvantage of using polonium 210 as the source of energy. So one aspect of this is that we need a lower mass. So sorry, where did this go? Yeah, okay. So we need a lower mass, 874 kgs, and this is 3.7 grams. No, wait. So we need 874 grams of this, and we only need less mass of this. Okay, so we can draw comparisons based on mass. So 874 grams of plutonium, NPO, okay, so EU, and this is just 3.37. Okay, let's draw a comparison based on half-life. that was 87.7 years, and this is 0.378 years, which is we can see how much years that is. Alright, and what else do we know? Okay. Now, one thing you have to remember, that power, we said power is directly proportional to activity. So the activity for this one will be very different from the plutonium one. How? Now we have the graph. Initial activity is the same. Initial power output is the same. So initial activity would be similar also. Now you have minus ln2 over 0.378 times by t. This, and compare this with ln2 over 87.7. So we can find out the value of lambda just to compare with this. So ln2 divided by 0.378, okay, so 1.88. So basically this constant that we have with e raised to power, that we were trying to figure that out. The graph can tell us, if we sketch a graph for that, we can tell us that. So the first one is e raised to power minus 1.833t, okay, for plutonium. This one is, oh no, sorry, this is the second one. This is the second one. Polonium, okay. Now we need the 87.7. Sorry. No, 87.7. See, this is going to be very short, small, 0.007 t. This means the rate of change. This is basically the rate of change. Because this is a constant, the rate of activity, dA over dt, basically, if you think about it, rate of change of activity is defined by this level, because this is the same constant that is going to come out if you know your differentiation. So proportional to, so this would be e raised to power minus 8333. Similarly, the other one would be proportional to minus 0.007 e raised to power minus 0.007t. Now, why does it matter? Because the graph is changing this way. So this constant changes the graph. It makes it more steeper, as we have already seen. This thing and this thing actually changes this. So this is this one. Sorry. Okay, let's say this is this one, and if I had to draw the other one, this one, the 87.7, this would be slightly, oh sorry, no, it would start at this way, but it would be longer. Okay, so this would be 87.71. So that means the plutonium one. So this means that the half-life is much shorter, so it will not last very long. Okay, advantage. So less mass, sorry, lesser mass. See, lesser mass of polonium is required for same initial power output, for same initial power output. So less amount of mass is required for launch. Okay. The other one was half-life of polonium is much short, so it will not last long enough. Okay, that's it. And that's it for this question also. Let's move on to the next one. Question number 9. Ultrasound is used to produce diagnostic information about the internal body structures. Explain how ultrasound waves are detected. Now, detected is a different story than produced or generated like that. Detected, they use the same principle as piezoelectric crystal, but the vibrations of piezoelectric crystal create alternating voltage. And that alternating voltage, the signals are then amplified and processed for that. However, that's the more we go into the processing part, that will become the imaging. We just need to answer how they are detected. So you see over here the detection of ultrasound waves. In ultrasound imaging, pulses of ultrasound are sent into the body and reflected by the boundaries between tissues. These reflected ultrasound waves return to the transducer when they strike a piezoelectric crystal. This impact causes the crystal to generate an alternating potential difference due to the piezoelectric effect. The generated EMF is then amplified, processed electronically. Okay, we don't have to answer about the imaging. I just added this sentence to finish this off for medical diagnosis. That's what we just have to simply write. So, pulses of ultrasound are reflected by the boundaries between the tissues. These reflected pulses reach the piezoelectric crystal and cause it to vibrate. The vibrations cause the piezoelectric effect. The vibrations generate EMF signal, same frequency as of ultrasound pulses. That's it. Okay. An alternating voltage V varies with time t according to V is equal to V naught sine omega t. The voltage is applied to an ultrasound probe. The root mean square RMS voltage is 66 volt. Frequency of the ultrasound generated by the probe is 4.3 megahertz. Determine the values of V naught and omega. So you see, remember we said that the EMF signal generated is of same frequency as the ultrasound pulse. So the omega that we will have over here will be will have the same frequency as this one. So first off, we need the maximum voltage. So we have the RMS. We know the formula. V is equal to V naught over root 2. So basically V naught would just be simply root 2 times by VRMS, right? So this would mean that we have root 2 times by 66. So root 2 times by 66. So this is 93.38. So let's call it 93. Omega. Omega is 2 pi f. So 2 pi times by f, we need to convert it into hertz. 4.3, 10 raised to power 6, because radians per second, right? So we need it in hertz. So 2 pi times by 4.3 times by 10 raised to power 6. So this is, let's turn it into standard form. 1, 2, 3, 4, 5, 6, 7. Okay. Table 9.1 contains information about air and soft tissue. Okay. Determine the unit for specific acoustic impedance values shown in table 9.1. So first off, we know that specific acoustic impedance is the product of density and speed of sound. So that means density is kg per meter cubed, and this is, sorry, let's see that, kg per meter cubed times by meters per second. So this would become kgs. The unit for that. So this would become kg, meter minus 2, second minus 1. Okay, calculate the density of soft tissue. Sorry, let's write it over here, rho c. Okay, density of soft tissue. Okay, so the product, we need to do that, okay. 1.7, 10 raised to the power 6, okay. So z over c, 1.7, 10 raised to the power 6, and divided by 1600. Okay, so 1.7 divided by 1600 times by 10 raised to the power 6. 1062, so let's say 1060. How much significant figures we have? 2. Okay, so I think we can round it up to 11. Okay, use the data from figure table 9.1 to explain why the ultrasound cannot be used to produce an image inside the air-filled cavity such as the lungs. Oh, we actually have to write it over here. So kg, meter minus 2, second minus 1, and this is 1100. Okay. So we need the data to explain why ultrasound cannot be used to produce an image inside the air-filled cavity, such as lungs. So we need to give the answer in terms of intensity reflection coefficient. So reflection coefficient would be z2 minus z1. So 1.7, 10 raised to the power 6 minus 4.3, 10 raised to the power 2 whole squared, and 1.7 times by 10 raised to the power 6 plus 4.3, 10 raised to the power 2 whole squared. So we actually need to use this answer. So square 1.7 times by 10 raised to the power 6 minus 4.3 times by 10 raised to the power 2. Okay, same values now, but with 10 raised to the power 6 plus 4.3, 10 raised to the power 2. So this is 0.999, you can say. So we will say that the intensity reflection, you can say intensity reflection coefficient is 0.999, or you can say intensity reflected is 99%. So intensity reflection coefficient is 0.999, which is almost approximately 1, meaning almost no ultrasound is transmitted into air-filled cavity. Okay, so no transmitted, so therefore there will be no reflections. Alright, and that's it for this question. Let's move on to the next one. Question number 10. A student observes different stars from the Earth. Give 2 reasons why some stars appear brighter than the others. Now, the brightness is similar to flux radiance and the luminosity, brightness things, intrinsic brightness, extrinsic brightness, apparent brightness, sorry. So they're similar, like similar quantities, but they are different. So why they appear, the factors are similar. So one is more luminous, and there could be the difference in distances also. So we will say that luminosity, so luminosity and luminosity of brighter star will be greater, okay, oh sorry, and proximity to Earth could affect the apparent brightness as a brighter star could be as a star that's closer may appear brighter. Okay, alright. State what is meant by a standard candle. A very common definition: an astronomical object of known luminosity. Okay. A spectral line from a star within a galaxy is observed to have a wavelength of 660.9 nanometers. The same spectral line measured in laboratory is observed to have a wavelength of this. Show that the speed of the star relative to the Earth is this. Okay, so first off, that means we need the redshift. So we need the speed of the star, so we need difference in wavelength over wavelength times by speed of light. So 660.9 minus 656.3 divided by 656.3 times by speed of light 10 raised to power 8. Okay, so 660.9 minus 656.3 divided by 656.3 times by 10 raised to power 8. So you get this 2.1 10 raised to power 6 meters per second. Exactly what we needed to show. Calculate the distance to the star. Okay, So we need Hubble's law, which is V is equal to H naught times by D. So that would be V over Hubble's constant. So V is 2.1 10 raised to the power 6 divided by 2.3 10 raised to the power minus 18. So let's use the same value that we had over here. 2.3 times by 10 raised to the power 18. The distance is 9.1 10 raised to the power 23. Okay. State and explain what can be concluded about the universe based on this change in observed wavelength. So this change in observed wavelength basically indicates redshift, and that means the object is receding from the Earth. So we can say that this difference in observed wavelength indicates redshift due to star or the galaxy moving away from the Earth. This means that the universe is expanding. Alright, that's it. That's all we need to say. Indicates redshift due to star galaxy moving away from the Earth, and this means that the universe is expanding. That's it. And that's it for this paper. If you liked our video, give it a thumbs up, subscribe to our channel, turn on the notifications. We also offer one-on-one coaching for A-level maths and physics. If you have any interest in preparing for May June 2026, whether one-on-one or as a part of the group, reach out to any of the social media links that we have given in the description. You can just navigate through the link tree that you see below the video and reach us out on WhatsApp to sign up for one-on-one. We offer one-on-one better. Groups, obviously we have to maintain the size of the group. We keep it to a minimum amount of students. So alright, anyways, if you have any questions, doubts or confusions from this video, this paper that we have attempted today, feel free to leave a comment, and I would love to help you out. If you think I made a mistake somewhere, I was unable to explain a certain question properly, also please feel free to tag the time and point out where you would love some explanation further. And do check out the Grade Booster Pack. You've already seen that I've shown you in this video how we have covered all the major questions already in the Grade Booster Pack. So until the next video, take care. Bye bye.